In this video, I want to sort of go over a little bit about vector addition. And let's just kind of cover this in some good detail here. There's a few simple situations you could run into when it comes to adding and subtracting vectors. The simplest is probably you have something like there's a vector going this way. Let's make it a displacement vector. So we're going up 2 meters, and we're going to add another 2 meters up to it. Your intuition probably serves you well here. We said 2 meters up plus 2 meters up. Well, that's going to be 4 meters up. The same general rule that we talked about for adding vectors still works here. Put the vectors head to tail and connect the tail of the first to the head of the last. It seems kind of like overkill for such a simple example, but see how it still works? Like the same general rule you can still apply. And there's the resultant, connecting the dots between the tail of the first and the head of the last. What if we had the situation, let's make it a force vector now. What if we had 15 newtons of force acting left and 10 newtons of force, I didn't draw that to scale, 10 newtons of force acting right? What is the answer here? 5 newtons left. If vectors oppose each other, they're in the exact opposite direction. The sign convention there is that we just sort of, make one negative relative to the other one. So we could say, well, this is like left in this case was positive, so this is negative 10. It's arbitrary, which direction you assign as negative, as long as you say when vectors oppose each other, one is negative relative to the other one. In general, we tend to make down and left negative in physics, but there's no rule that says we have to do that. Sometimes I like to make down positive, like when we're doing gravity problems, so we know things are falling down. I always like to work with positive numbers if I have a choice. And so I'll just say, well, down's positive in this situation. So it's up to us, as long as you keep track of vectors that oppose each other. So adding vectors that are in the same direction or opposite directions, kind of easy. This is a little bit harder. What if it goes at right angles to each other, like due north and due east? Then you got to call in Pythagoras' theorem, right? Because then we don't just say, oh, 11 plus 11 is 22. We say 11 squared plus 11 squared is equal to the resultant squared. And so the answer is actually the square root of 242, which is 15.6. It's not 22, right? If you go 11 kilometers north, take a right turn and go 11 kilometers east, you've traveled a distance of 22 kilometers, but your displacement is only 15.6 kilometers. This was like the example we saw of a girl who ran 120 meters north and 80 meters east, right? And her velocity was different than her speed, right? Because her distance was different than her displacement. So adding vectors at right angles, we use Pythagoras' theorem. Now, in a tougher problem still is if we have vectors that are like this. Okay. So vectors like this are neither aligned with the x or the y axis. Like vector A goes up and to the right. Vector B goes up and to the right. So we can still use the rule of A plus B is the resultant. I connect them head to tail, draw a line from the tail of the first to the head of the last one. So that still works for that general rule. But how could I calculate the value of R? Here's where we need to be introduced to an idea of resolving vectors. So vector A is moving up and to the right, and it's up at some angle. Let's call it theta A. And vector B also is up and to the right, and it's sort of at some angle theta sub B relative to the horizontal. The way to add these vectors is to first resolve the vector into x and y components, we say. In other words, we take a hypotenuse and we break it down into an x component, a horizontal component, and a y component, a vertical component. Okay, we do the same thing to this vector. In other words, we're forcing this problem into a simpler one because we know how to add vectors that go in the same direction. So if I have two vectors that both go up and to the right, but sort of by a different amount, I need to figure out how much of this goes to the right, how much of this goes to the right. And then I can add those up because I know how to add vectors that go to the right. Like vector A brings me over this far. Vector B brings me over the rest of the way. And so AX plus BX equals the X component of my result. Okay. Likewise, A brought me up this much. That's my A sub y component. B brings me up sort of the rest of the way. So my A sub y plus my B sub y, the y number, equals my resultant in the y direction. So I've got my resultant y. Once you've done all of that, you've resolved the vectors into x and y components and you've added them up, you can construct a new right triangle. There's my r sub y. There's my r sub x, right, which is just the sum of my x's and y's respectively. And then my resultant r here, I can solve again using Pythagoras' theorem. In other words, you turn it into that problem, that example we just saw a moment ago. So I'd be able to solve for the resultant here by using r sub y squared plus r sub x squared equals the resultant squared. And then just using Pythagoras' theorem to solve for r. So that seems like a lot, okay? And it is, but the only other way to solve one like this is to know something like the law of sines. And then you have to know, I think, kind of like the angles therein. And you can say it's like the sine of this angle over that side length equals the sine of this angle over that. So look it up. The law of sines will work for problems like this, but you have to kind of know, I think, a number of angles to solve it that way. You want to get used to resolving vectors because we'll do that a lot in this class. So what do we mean by resolving the vector and how do we do it sort of computationally? Let's look at an example here. I've already sort of worked through this example, but while we're talking about it, let's queue up this one right here. And so we've got water that's going this way along this river, and the boat that's going to go this way at 3 meters per second. Note that it's at 60 degrees. Now, this isn't exactly the toughest example problem because at least our water velocity vector is going directly to the left. It doesn't have a component up or down, but this vector does. So we have to resolve this vector and realize that if the boat sort of leaves the riverbank this way, maybe the boat captain was hoping, well, I need to cross the river, but because the water is pushing me this way, I'm going to head off sort of in that direction. All right. So we need to solve the magnitude of the resultant velocity of the boat. The boat's going this way, the water's pushing it that way, and so we know how to add vectors. This vector, the tail of it is here, it's pointing in this direction, so the head of the vector is right there. I'm going to place this vector, the water velocity, head to tail with it, and this one is actually to scale. So another way to solve vector problems is to actually use a scale drawing. Like I could use my ruler if I had this like in front of me on a piece of paper. I could measure that and say, oh, that many centimeters is 1.8 meters per second. This many centimeters is 3 meters per second. And kind of set up a scale so that when I connected the dots, right? Because remember, the resultant is this one right here. I could actually measure it with my ruler and say, oh, I already know how many, meters per second represent each centimeter, and use your scale to solve it that way. So you can actually solve it with like rulers and scale drawings. We're going to solve it with the vector resolution that I just mentioned a moment ago. So this vector, the boat velocity vector, is going up and to the right, which means it has a component to the right and it has a component up. I'm going to call the component to the right the velocity horizontal, and I'm going to call the component up the velocity vertical. So I got a vertical and a horizontal velocity. These are the components of the boat's velocity that I'll just call v. And I know the value of that, it's 3, right? The boat velocity is actually 3. The hypotenuse of this right triangle is 3 meters per second. If I want to know the value, how much of this 3 meters per second is going to the right if it goes up and to the right? How much of it is horizontal? Then I would realize that this side is adjacent to this angle. And I can remind myself that the cosine of some angle, in this case 60 degrees, is equal to a ratio of sides. It's equal to the adjacent over the hypotenuse. The adjacent is the thing I want to know, the horizontal component of velocity. The hypotenuse is 3 meters per second. A little bit of algebra. Bless you. And I can calculate the horizontal component of velocity is equal to 3 meters per second times the cosine of 60 degrees. If you need a calculator to prove to yourself that the cosine of 60 degrees is a half, go ahead and take one out and type that in. Some of you might just have that one memorized. That's kind of a famous one, like cosine 60 is a half. So we know that half of 3 is 1.5 meters per second. The boat sets off this way with velocity up and to the right. And how much of it is to the right? 1.5 meters per second. That doesn't mean, oh, then the vertical is also 1.5. That's not how we add things at right angles, right? We add them with Pythagoras' theorem. You could use Pythagoras' theorem to solve for this now, because we know 3, we know 1.5. But since I'm already using some trig, let's solve this with the trig also. The vertical component of velocity is opposite the 60-degree angle. There's a function that relates the side opposite to the hypotenuse. And it's the sine function, right? The sine of 60 degrees is equal to opposite over hypotenuse. So I can write this. Likewise, how I solve up here, multiply both sides by 3 meters per second, and I can calculate the vertical component of velocity is just 3 meters per second times the sine of 60 degrees. Now you probably do want to have a calculator out. Let me show that to everybody following along at home. Trigonometry. We need a sine function there. There's the sine of 60 degrees, and I'm going to multiply it by 3, and I realize that the vertical component is about 2.6, right? 2.598. So 2.6 meters per second is the vertical component of the boat velocity. Now I want to solve for my resultant, right? Remember, I've already added them. I added this plus the boat velocity, or the water velocity, right? This is the water velocity over here, 1.8 meters per second of water. I just moved it so it's head to tail with this vector. You can translate a vector anywhere in space. Like I could draw the water velocity down here if I wanted to. It still is that magnitude, right? I still draw it this long, 1.8 meters per second. I still got it going to the left. How much and which way? So you can move a vector anywhere in space that's convenient to solve. I moved it so it's head to tail with this vector, so I can see my resultant like this. What is the net horizontal velocity of the boat? What's the resultant horizontal? Anybody have that? If the water is pushing it 1.8 meters per second to the left, but the boat itself is going 1.5 to the right, there's a net velocity of 0.3 going that way. In other words, here's my new hypotenuse, my resultant, and it consists of legs that are 0.3 meters per second that way, and how far up? The component up just came from the boat velocity, the 2.6. In other words, the water velocity doesn't contribute to the vertical resultant, right? All the vertical comes from the boat velocity, and we know that's 2.6. So what I can do is realize, here's my resultant. It's some vector that kind of points a little bit to the left, right? It's like 0.3 to the left, and it was 2.6 meters per second up. Okay. So now I should be able to calculate the magnitude of the resultant velocity of the boat. I know it's going 2.6 up, it's going 0.3 to the left. I've added the boat's velocity to the water velocity by resolving the boat velocity into its x and y components, into its horizontal and vertical components. So now I can just use Pythagoras' theorem. 2.6 squared plus 0.3 squared equals. And so it's nearly going to be equal to 2.6, right? Like that's a small sort of contribution to the total velocity. And in fact, what I could do is keep this value in my calculator, so it's a little bit more precise. And so the sine of 60 times 3. This 2.6, remember I rounded it. It's actually 2.598, whatever. So I'm going to take that in my calculator, 2.598 squared. So that's 6.75 plus 0.3 squared is 0.09. And that's going to equal my new resultant squared. 6.75 plus 0.09 is 6.84. So 6.84 is what the resultant squared is. And if I take the square root of that, I realize it's 2.62. All right, so this one's going like 2.59. This one's going like 2.62. Because there's a little bit of speed, you know, a net speed to the left, because the water pushes us to the left a little bit more than our boat, you know, moved us to the right. Take a moment now and change these letters to these letters. Velocity equals 2.6. All right. So when you round it, you know, it ends up just being 2.6 anyway. So see that you can solve it either with the scale diagram or components of boat speed determined parallel and perpendicular to river flow. That's what we did. We used components of the boat speed, right? We resolved that vector into x and y components. Let's try one like this to really drive this point home. Vector A, you guys want to do a displacement vector, velocity vector? What's the liking of the class? What kind of vectors do we want to add here? Displacement. Let's say the displacement here is, can we do like space travel? I'm an astronomy teacher, I don't know what space travel. Let's say that this displacement is, well, no, we'll keep it down there. And let's not do some conversions, okay? Let's just make it straightforward here. So we'll say the displacement here is 23 meters, and this angle right here, theta sub A, is 25 degrees above horizontal. Vector V over here, well, that's 17 meters, and its angle is more like 62 degrees relative to the horizontal this way. What is the value of the resultant displacement? Let's work through that together. The first thing I want to do is resolve my vectors into their x and y components. So I'll start with vector A. If vector A is moving up and to the right and its hypotenuse is 23 meters, then the x component of A we can get from the cosine function, right? So the cosine of this angle is equal to A sub x over the hypotenuse 23. The cosine of the angle is equal to the adjacent, right? The x component of this vector over the hypotenuse, which I know is 23 meters. So I can readily solve that a vector that moves 23 meters, that's 25 degrees above horizontal, has how much of it going to the right? So everybody with a calculator knows that the cosine of 25 is 0.906 times 23, and I realize that the x component of vector A is 20.85, we'll say, we'll round it to that, meters. How about the y component of A? How far up does it go? Well, that's opposite. A sub y is opposite my angle. So what function relates the opposite and the hypotenuse? That's the sine function. That's the SO in SOHCAHTOA. So the sine of 25 degrees equals opposite over hypotenuse. And now I can solve for the y component of vector A as 23 meters times the sine of 25, right? Just multiply both sides by 23. So the sine of 25 is 0.4226 times 23, and I realize that I'm going up 9.72 meters. Because if you go 23 meters this way, but you're going at 25 degrees, you've only gone up, north in this case, 9.72 meters. Now I know that vector A brought me 23 meters this way, and that's equal to 20.85 meters east and 9.72 meters north.
Teachers, at this time, please release the 11th grade students to the auditorium. All 11th grade students, please report to the auditorium for your class meeting.
All right, so when future historians are looking at this YouTube video, realizing what was going on in the 21st century early on, they'll say, oh, this class was just dismissed to go to the 11th grade meeting. But I'm going to keep on going, YouTube, for your benefit and for all those physics students out there. So check YouTube later, you guys. If you're an 11th grader and you're going to that meeting, we're going to finish off this calculation here. We're not going to be stopped by some meeting. We're going to keep the physics going. All right, have a good rest of your day. Quiz tomorrow. On to vector B now. So we've got the x component of vector B that we're going to solve the same way that we solved this one. So we've got the cosine of 62 degrees equal to b sub x over 17 meters. So the x component of B is going to be cosine 62.469 times 17, and we get the x component equal to 7.98 meters. Now we'll solve for the y component of B. That's going to be the sine of 62 degrees equal to b sub y over 17 meters, because that's the hypotenuse that we assigned for vector B. So 62, sine of 62 is 0.882 times 17 to give me about 15.01. And so b sub y is equal to 15.01. Now I've resolved those vectors. And so I can just sort of add them all up now. I can say, here's my vector R, and it goes over 20.85 from A, and another 7.98 from B, right? Those are my x components of vectors A and B. So I add up my x's. So 20.85 plus 7.98 equals 28.83. So I have a new, I'm just going to kind of redraw this over here. So I have my resultant R, and I know that it's the sum of A and B, AX plus BX, which is 28.83 meters. Now let me add up my Y's. So my Y's were 9.72, remember, from A, and 15.01 meters from B. So I'm going up here, 9.72 plus 15.01. So that's 24.73 meters up. Okay, 9.72 from A, 15.01 from B equals 24.73 up. We'll get rid of some of this work in here and make it a bit more clear. All right, so I had the sum of my x's, 28.83, the sum of my y's, 24.73. Those are now new legs of this right triangle, where now I can use Pythagoras' theorem to solve for r, right? So it's going to be 28.83 squared plus 24.73 squared equals r squared. Let's write that out down here. 24.73 squared plus 28.83 squared equals r squared. 24.73 squared is 611.5729 plus 28.83 squared is 831.1689. So the sum of those is 1,442.7418. And the last step would be to take the square root. And so the value of R is about 38, 37.98, meters. That's the calculator value. And I would probably just round that to 38 meters, because if I go 23 this way and 17 that way, I've really traveled 38 meters, but in what direction? I still haven't solved for the direction of this vector right here. So a simple thing to do would be, since I reported these angles relative to sort of the positive x-axis, I kind of want to know what this angle is right here. What's my theta for R? The easiest way to do it might be to sort of solve for this angle right here. We'll call it phi, because I already know the opposite and the adjacent. And so I could simply take inverse tangent of opposite over adjacent, right? This is the side opposite of phi. This is the side adjacent to phi. So by solving for this angle phi and realizing it is a complementary angle to the one that I kind of want to know, I can solve it that way. So 28.83 divided by 24.73 is equal to 1.16, and the inverse tangent of that is 49.37 degrees. And so this angle here is 49.37. So that's the angle that it makes with the vertical. If this much is 49.37 degrees, well, how much does R open up from horizontal, from the positive x-axis, the way that we've sort of written these? Well, it would just be 90 minus that, right? Because those are complementary angles. And so the angle, the sort of the final answer is that vector R is 38 meters, but its angle right here is 40.62 degrees above horizontal. So we could sort of say that our final answer now, vector R, is 38 meters at 41 degrees, and you could say north of due east, or you could say above horizontal at 41 degrees. I'll say north of east, because the x-axis is like due east, and we've opened up our angle 41 degrees from there to know the direction of R. So that's using vector resolution to solve vector addition. If you have vectors that aren't perfectly aligned with X and Y, you have to resolve them so you can add up the X's, add up the Y's, put it back into a new right triangle, or you can use Pythagoras' theorem to solve for the magnitude, the hypotenuse, and you can use a trig function to solve for its angle.